We have another fun topic to discuss for today's session. Let's start with the question. Here we have, I think, the question on magnetic fields or the general concept of electromagnetism. A uniform magnetic field B is directed into the page and exists in a circular region of radius d. A single loop of wire of radius capital D is placed concentrically around the magnetic field region in the plane of the page. The initial magnetic field strength is B naught. Calculate the following terms. Calculate the following, in terms of given values and fundamental constants. Let's start. So part A asks us to calculate the initial flux through a loop of wire. We know that flux for any field, whether it is electric or magnetic, is given by the general formula. Flux is equal to field or the strength of the field multiplied by the area through which the field lines pass through and the cosine of the angle theta, where theta is the angle between the field lines and the normal drawn to the particular area. Here, since the field lines are passing perpendicular, the normal and the field lines will make an angle 0, which means cosine of 0 is 1. We don't have to worry about that. The initial strength of the magnetic field is said to be B naught. So assume B naught into the region is in the shape of a circle with radius D, giving me the area pi d square. Moving on to part B of the question. Part B tells us that at time t equal to 0, the magnetic field strength is a function of time given by the equation B in function or in terms of t is B naught into t square, where B naught is a positive constant. Determine the magnitude of induced EMF in the single loop. The magnitude of induced EMF or electromotive force is given by Faraday's law under electromagnetic induction, which states that the induced EMF is equal to the negative derivative of the magnetic flux with respect to time. If the number of turns are n, then we have n times the particular value. Since it is just given to be of 1 turn, we will ignore the value of n or assume it to be 1. So we get the answer as minus d by dt of or differential with respect to t of B naught into t square into pi d square. And simplified further, we get the EMF to be exactly equal to negative B naught is a constant, comes outside. So negative B naught into pi d square into differential of t square. Differential of t square is 2t, giving me this particular answer. Or the magnitude of EMF is just B naught into pi d square into 2t, or 2b B naught pi d square into t. Moving ahead, let's answer part C. Determine the direction of the induced current in the loop. So here, the magnetic field strength B that is produced is assumed to be into the plane of paper. We understand a concept known as Lenz's law, which tells us that the induced EMF due to the changing magnetic field is such that the induced current will produce its own magnetic field that opposes the changing magnetic field which is causing it. Here, let me show the correct depiction. I seem to have shown the wrong depiction here. The depiction is that the magnetic field B is into the plane and the induced EMF on this single loop of wire will be such that it produces a magnetic field that counterbalances it, such that the induced magnetic induced current produces a magnetic field that is supposedly out of the plane. This direction of magnetic field produced by the induced EMF through the right hand grip rule or the right hand thumb rule gives us the correction of induced current to be counterclockwise. The direction of induced current is counterclockwise. So to sum up, the direction of current is counterclockwise because the counterclockwise induced current produces a magnetic field that is out of the plane, which tries to stop the changing magnetic field that is into the plane, which is causing it in the first place. This is an understanding from Lenz's law. Moving on to part D. Determine the energy dissipated in the loop up until a given time T1. So let's try to understand this. We know that power instantaneous is given by the formula P equals V square over R. And here, since voltage V is nothing but the induced EMF, we have power P is equal to V square, V naught square, pi square, d power 4 into 4T square divided by capital R. We also know that the power is the rate at which energy is consumed. So total energy consumed or total energy dissipated is derived as follows. P is equal to a differential of energy. Let's denote energy by capital E, dE by dt, or total energy E is equal to integral of E into dt. The limits of integral here are as stated in the question. That is 0 to up until a value of T1. We know the power equation given by B square into pi d power 4 into 4T square over R. Here, B square or B naught square, pi square, d power 4 and R are constants which come outside the expression. 4 also comes outside the expression. So we just end up integrating T square with respect to T. The integral of T square with respect to T is T cube over 3, which gives us the total energy dissipated as a function of time T1 as E is equal to 4 B naught square into pi square into d to the power of 4 into T1 the whole cube, and the limits of the definite integrals are applied over 3 times R. This is the entire expression for energy dissipated up until time T1.